the whole material is, for example, a certain type of sand, or certain type of rock, or certain type of soil, whatever. For example, we have different. This is the ground, this is the crush, and this is, for example, the ground surface. We have different layers. For example, from the soil engineering, you saw it. We have sometimes we have clay, sometimes we have sand. One of them is strong, one of them is weak. We have different types of layers, and the behavior of the behavior of wave in each layer is different from uh, the other layer. So, for example, this is the point of action, or the point of crush, or the point of release of energy, and this is the wave. When this wave reaches this layer, a part of it passes to the next layer, and a part of it reflects. Okay. Again, in this layer, and you should know that, I think you know it from the movement of, for example, light in water. Sometimes we have this one, and then we have uh, the wave is, for example, like this, then like this, then like this. That's one of the reasons that we have rainbow. So part of this uh, reflects, and the other part passes to the next layer. We have, for example, again in here, we have such thing, and for example, this thing. Again, we have this one and this one. So the movement of the waves, these waves, underground is unpredictable, or it's very, very complicated, and we can't predict it at this time. Maybe in future, but right now, because we can't uh, we don't know the exact material of the soil below the surface, or even if you want, we have to perform very, very complicated analysis, for example, using ultrasonic waves to find the exact behavior of the soil. After that, because we don't know the exact pathway of this wave, so we can't predict it. For example, at this point, we have shakings, and for example, we shouldn't uh, construct our building here. The thing that we already know is that we have to avoid constructing our building near the faults. I told you what was fault.
Sir,
But
your voice and your writing are not coming at the same time. Can you wait a little bit?
maybe because I'm uploading this video, that's why. Uh, Wait for 5 minutes. That will be better.
When you say at this point, we cannot see this point.
Okay, because it's 8%, 85% here. I think because of this uploading, because I'm uploading the previous video.
Okay.
I'll talk a little bit slower. Um, Now I want to talk about acceleration. Mainly we show it with A, but when it comes to earthquake, we show it with G. The unit is meter per second square. Okay. If you remember, I told you before that the earthquake mainly the thing that the thing that is important for us is the ground acceleration. How? Because the earthquake itself is not dangerous. Okay, the weight, the combination of mass and acceleration from the second law of Newton, the combination of mass and acceleration leads to force F equal ma. So if you construct a building, for example, if you are living in a building, in a massive building, uh, or this is, for example, a massive building, or the other, for example, this is a person living in this building, and the other person live in a tent. I don't know how to show it. For example, something like this. Okay, tent uh, made from, for example, I don't know, for example, silicone, whatever fibers. This comes from concrete and steel. Okay, and for example, one of them is they both are in the same area. Okay, they both are in the same area. For example, they both live in this area. When I'm saying that they both live in the same area, I mean the soil type and, for example, the waves that uh, right here are all of them are same. Okay, so the massive concrete, for example, the weight of this structure is about, I don't know, for example, 100 or 1,000 ton, and the weight of this tent is about, for example, 5 kilograms. Okay, the earthquake force P or F is equal to m dot ag. And because the a or the acceleration is not a constant thing, it varies with time, we show it with this. Okay, we can say, for example, the ground acceleration is whatever, for example, is 3 meter per centimeter per second. So we can't say that because it varies with time. For example, this is, I showed you once, this is the acceleration. For example, at time at t equal to 5 seconds, we have, for example, this acceleration at t or at time equal to 10 seconds, we have this acceleration at time equal to 15 seconds, we have this acceleration. So we don't have a constant or a uniform load. So as I said, the people living in this tent are safe. I'm assume that the earthquake is the earthquake doesn't uh, rip off the ground, just the shaking. Okay, so we have shaking. just shake. The other people living in this experience a force equal to 10 or that, for example, what was, for example, at time equal to 5 seconds, the acceleration is 3 meter per second. So the people living in this building experience this force, and the people in this tent experience 3 dot m acceleration is 3, and the mass is 5 kilogram. So you'll see that this is the reason of, or the danger of the earthquake is because of the acceleration. Okay, so the thing that transmits to the structure is acceleration, not force, not displacement. The dangerous thing is the acceleration. And it's obvious one of the methods that we use to reduce the earthquake effect is what? Reducing the weight of the structure. Okay, for example, we have lightweight concrete, we have uh, lightweight, for example, lightweight roofs, many things. We'll talk about it in future. But right now, I'm saying that this is the earthquake force, and that's why we, in all the reports, earthquake reports, we report acceleration like this, because if we know the acceleration, for example, in ETABS, in SAP, in whatever, if we apply, if we uh, enter the acceleration, we can have the force, and then we can design our structure against this earthquake. How's the quality now, Shahlo? Is it better now?
Yes.
Hey, Dennis, I'm uploading the video. Let me see. Okay, I'll do it later. Anyway, uh, so um, as I said, this is the earthquake force. Do you remember from, for example, the engineering mechanics? If you remember, for example, uh, we had a cable like, and we had, for example, column like this, and we had a force like this, for example, 50 Newton. What was the first step? If you remember, the first step was free body diagram. To what? To analyze this structure. We have, what was the next step? For example, if you remember, I told you that you have to add the effect of this load like this, F, and the reaction of the ground, and the force, then sigma Fx equals 0, sigma Fy equals 0, sigma M equals 0. So uh, by knowing these equilibriums, you can analyze this structure. We have such thing in our structure under the earthquake or subjected to the earthquake. For example, this is our building. And as I said, we have a ground acceleration like this, AG. The weight of the building, where is the massive part of the building? Do you know? Who knows? The massive, you should know that the massive part or the main weight of the structure is concentrated in the roofs or floors. You can easily check it with your home. Take a look, you'll see that. For example, your roof has, for example, 10 centimeter or 5 centimeter of concrete, reinforced concrete, something like this. Reinforced concrete, and the main weight is concentrated in the roof. So because of this, we have a model like this. To make this simple, or to simplify this building, because it's not easy to model this or it's not easy to analyze, we have to simplify this structure. How? There is a method, we call it lump mass. In this method, we assume that the whole weight is like this. The whole weight of the structure is like this, a concentrated mass, a lump mass. And this is the ground acceleration, AG. So far, we have the weight and the ground acceleration. What next? When you have shakings, when you have earthquake, you should put something in your structure to resist against the earthquake. In concrete structures, we have shear walls. In steel structures, and even in concrete structures, we have braces, we have dampers, we have a couple of things to reduce the weight, to reduce or to resist against the earthquake. I showed you one of them, braces, for example, or shear walls. Shear walls are thick, strong concrete walls. We use them to resist against earthquake. And these elements add stiffness to our structure. For example, suppose that you have a spring. You remember the force in the spring? F is equal to Kx. You know that? Rafiq? You know that?
Yes, teacher.
So, what was that? Okay. Stiffness coefficient. Stiffness coefficient. The coefficient of stiffness. For example, sometimes you have a loose spring with a coefficient of 10. In the other case, you have very tight and strong spring with a coefficient of 100. This spring provides, if you move this spring, for example, 1 centimeter, and this one again 1 centimeter. This one provides provides higher forces. This one is 100.1, Kx is 1, K is 100. This one provides 10.1. You can see that the force in the stronger spring is 10 times higher than the other one. These springs are the exact, or we can consider, or we can assume these springs as these elements, shear walls or braces. So they are resisting elements, and we show them in our model. So the first one is lump mass, lump mass. The second one is spring. Okay, or let me show it in this way. This is our structure with the weight of m, lump mass. This is the ground. This is the spring. So what was m? I'm simplifying this complicated structure. Okay, I showed the roof, as I said, not roof, the masses of this structure with this box. Okay, I'm showing these elements such as braces or shear walls with this spring. Okay, we have other thing that we call it damping. Do you know what is damping? Do you have any idea? Abdul Hussein, you hear me or not?
Yeah, I'm hearing you. Dumping is pressing someone hardly.
Pressing someone? No.
Uh,
For example,
not someone, something.
anyway, for example, I think you all saw this thing. For example, you may have some clocks.
You know, did you saw Stammer, big machine for flattening iron? I don't know.
I know what you're saying.
I saw when
This is
on the
dumping.
fabrics.
That one is dump. This is damp.
I don't know.
Okay. For example, you have such thing. If you put, for example, if you release this hang from here, after, for example, 10 times, its energy damps and it will stay in this situation. You all know that. Yes? It's obvious. The reason is friction between this and air. Is it obvious? So we have friction between air, and this friction damps the energy. So at first, you have, for example, 100 joule, but at here you have nothing. Or we can say that at here we have 100. Yes, we can say it right. So in here it is not moving anymore. Why? Because its energy damps. As I say, the main reason is friction in this case. Okay. So we have a couple of mechanisms in our structure that damp the energy. One of them we can say that are bricks. How? For example, this is your building. This is the first column and this is the second column. What is between these columns? Your walls, brick walls. Yes? You have bricks, you have blocks. And within the earthquake, these bricks, these columns, because of the earthquake load, push these bricks, and because of this pushing, they move even a little bit uh, along each other, alongside each other. And this movement produces friction. Okay. The other thing that we can say, for example, if you have a connection, I showed you in the previous class. For example, you have a bolt connection. Inside this bolt, for example, you have this is hole and this is a bolt inside. Okay, the movement between these bolts and these holes reduces energy or produces friction, for example. All these absorbs energy, and we call this absorption, we call these energy absorption damping or energy damping. So as I said, we are completing our model. This one was K. The stiffness, I modeled this mechanism with spring, and I'm gonna model the damping effects with a damper like this. We show damper with D, and the coefficient is C. This is the coefficient of damping. So do you have any questions so far?
No, teacher.
You sure?
So what's the C? Did you near the C?
Coefficient of damping.
Signature. Coefficient. Okay.
Coefficient of damping. For example, this one is
right
coefficient
side
of
of the C. Right side of the
what?
right side of the C. The picture.
Right to this one, we call it dash pot, like this.
Dash pot. What's it?
Do you know what's pot?
Pot. Yes.
This is pot.
Something like foot.
No, this is pot. You put tea inside. Yes?
Yeah. I know.
This is pot. And if you move something, for example, suppose that you have a glass filled with honey. Okay?
Yeah.
If you move, for example, your spoon inside this glass, what would happen? The honey, it's not easy to, it's not easy to
Yeah,
spoon.
I get. Yeah.
Okay?
Yeah.
That's the reason we call it, this is pot and this is dash pot. It's like this because when you increase your force, for example, if you move if you move this spoon in a glass of honey, if you increase the speed, okay, the honey will push you back. For example, we have such thing in the swimming pool. Okay, have you ever tried to run inside the swimming pool? You can easily walk inside the water. Okay, but if you start to run, the water will push you back. This is the other definition of damping. So if you increase the energy, something such as water, such as I said, bricks, such as the friction between the connections will push you back. So these are the good thing. I mean, damping and stiffness are the good things. The bad thing in earthquake is ground acceleration. Abdulsen, if you're not talking, please mute your. Okay, so far, as I said, we simplified or we modeled this complicated structure. Or let me show it in this way. We have it here. This complicated structure with this simple model. Okay. Instead of columns and shear walls and braces, we have a simple spring. instead of bricks, instead of connections, instead of uh, some anything that absorbs energy, we just have this dashpot, or we have this damper. Instead of this complicated mass, we have this box, and this is our model for this structure. This is the simplest model. You can't design a tower, such as, for example, a flame tower, using this model. But you can design, for example, 1 or 2 story building with this model. So, uh, yes. From this model, we can analyze something. K and C. Free body diagram. Okay, suppose that, or let me, to make this better, let me write it in this way. This is your weight, this is your spring, and this is your dashpot. Okay. Suppose that you have an earthquake like this with an acceleration of AG, or ground acceleration. Okay. What is the first step? Free body diagram. The important thing is this mass. So you have to see what type of forces are acting on this mass. So this is your mass. Let me write it here. What was the first force that I told you? P is equal to M AG. As I said, this force is a bad thing, earthquake, but K or C or this spring or this damper are good things. So suppose that the earthquake is pulling this box, but this spring and this damper is pulling it this way. Okay, and they're not gonna let this structure to what? Take apart. Okay, so if you build strong columns, or if you provide some mechanisms, some damping mechanisms, you can save your structure. Okay, because you should keep the structure, for example, here. You should keep it here, and you should not let this mask that represents your structure shake a lot. Okay, so in here we have Fk, this is Fc, or we can, or in the other we can show it with Fs or Fd, and here you have your force. So sigma Fx equals 0. One force in this direction, P, the other forces are in the other direction, Fs plus Fc. Okay, so if you can provide this equilibrium, you're safe. If not, you're screwed. You'll see collapse in your structure. What are or why we should use this equation? Because at the first, for example, we can predict. For example, I told you that. For example, you live in this area. This is, for example, I don't know. For example, this is your city, whatever. This is the city, and you know that in 100 in past 100 years, the maximum shake for the maximum earthquake had the ground acceleration of, for example, I don't know, for example, uh, 4, 4 meter per second square. Okay, and for example, you want to design a building like this. You have the dimension, okay? You have the dimension, and you know you're gonna use concrete, you're gonna use steel or whatever. So if I tell you, for example, this dimension is 5 meter and this one is 3 meter, and you are using concrete, what is M? With a thickness of, for example, 5 centimeters. If you have the weight of this part, as I said, roofs and floors are the massive parts. So what is weight? Gamma dot volume. Gamma is the specific weight, or again, M over V is equal to rho. If I tell you, for example, the specific or the density of the concrete is 2.4, for example, and your weight is whatever, I don't know, for example, anything, what is the M? Rho dot V. These dimensions are given. Okay, these dimensions are given, so you know it from the beginning. You know, for example, you're gonna construct, for example, 10-story building, and your ground uh, dimension is whatever, so you can easily find M. As I said, you can check the record, the earthquake records, and see that the maximum ground acceleration here, ground acceleration, for example, within past 10 years old, within past 100 years, it's 4 meters, 4 meter per second square. So P is okay right now. What was P? M dot AG. For example, you know, you want to design your columns. What was, we simplified columns with springs. So the target is to design your columns. Also about the damping, you can't do many things, or it's you know, because somehow is restricted. Mainly we assume 5%. We also show damping with Xi. Okay, Xi. Mainly we have 5% damping in your structure. What does it mean? That means because of that bricks, I told you about the bricks, about the connections, about any friction mechanics in your structure. For example, if you have, if your input is 100 joules, because of all these mechanics, you can absorb or you can dissipate 5% of this equation, 5% of this energy. So your input is 100. What is your output? 95 joule. 95 joule. Yes. When I'm talking about 5% of damping, or psi is 5%, this is what I'm saying. What I'm talking. So the damping is somehow restricted. So you can't do anything about it. Not anything, much thing. The thing that is your target is K, or stiffness. So you have to provide your columns, you have to provide your beams, you have to provide your braces, shear walls, in a way that by using these columns and these elements, you can damp or you can resist against these forces. I know that it's a little complicated, and I'll talk about it later again. So, do you have any question about this part?
Can you review last part?
Last part, which part?
This construction 555.
Review.
This example.
Uh-huh. I told you that, for example, you live in a city. Right now, I don't have any record, but I'll show you in future. For example, it says that the dominant or the strongest earthquake in your city, for example, was this. Okay, and in this earthquake, the peak of the acceleration is 0.3 g. How much is g? 10, for example. I assume that it's 10 meter per second square. So the peak ground acceleration, peak ground acceleration is what? 0.3.10, 3 meter per centimeter square. Okay, F is equal to ma. Suppose that you want to design a building like this. You all know that the specific weight of concrete is 2,400 or 2,400. For example, you assume that the thickness of the floor is 5 centimeter. This dimension is 3 meter and this dimension is 5 meter. If I ask you how much is the weight of this floor, we can say that the volume is 5 meter, but 3 meter, but what? The thickness. Thickness is 5 centimeter. I'm gonna write it in this way. This is the weight, kilonewton per cubic meter. So, or the mass of the concrete or the density of the concrete is, for example, let me write it this way. Kilogram per cubic meter. Okay. So rho is equal to m over v. This is v. This is clear, Shablo? This is clear.
Yes.
And m as a what and rho. This is given. You once I remember that once you found this specific weight of concrete in lab, if you remember, using oil. So m is equal to rho dot v. This is rho and this is v. So you have the mass. F, as I said, is equal to m over a, or P is equal to m dot ground acceleration. The peak ground acceleration is 3, I showed you. M is, for example, whatever. For example, I don't know, whatever m. This is the first side of this equation. This side. So P is known right now. I told you that many researchers found that this part, I mean damping, is not more than 5%. Okay, is not more than 5%. So I'll explain this part more in future, but for now, assume that this part is known as 5%. Okay, I'll explain it in future in detail. So you have this part and you have this part. You can find this part. It's easy, yes. P minus F. C gives Fs. And if you know the force, you know you can design your columns and walls. Okay, so for when you want to design, for example, a column, you should know that you want to design it for what load. What is your applied load? So if you know the force, you can design this column, and this is your final target as a design engineer. For example, in the previous class, I showed you that, for example, how to design tensile member. In future, I show you how to design a column. So at the final step, you have to check your capacity with this load. I'll explain it in the future. Don't worry about this one. Any other question?
No.
Okay. See you next time.